Hi everyone. In this lesson, we will continue with the ideal derivative compensator or its design in root locus techniques. Okay? And so, firstly, we should write that the manipulation of transient response, which is related to the derivative term, okay? Because in the steady state, we will focus on to integral control, okay? And so can be accomplished by selecting the PD as the setting, the pole or poles on root locus, right? And so how we can do that? We need to define another controller in here, G controller S or D derivative controller S should be equals to the what? The S plus 0 C. Okay, these are the basic form to drive the derivative compensator. But in order to understand the effect of this addition to your system, we need to build or solve the our MATLAB code on the root locus techniques. Okay, so in order to do that, we need to create another script in here, just like this one. So as always we do PD zeros effect on closed loop transfer function. Okay, and always we need to add the clear all, close all, CLC. Okay, where 3 PD zeros effect. These are the name for the code. Okay, and so firstly we need to give the x1 in here, just like this one, to define normal PD design with zeros. Okay, and zeros z1 must be, for example, -2 is the 0 in this place, poles z1 the for example -1, -2 and -5. Okay, and again z1 can be selected as the 1. Okay, because we need to draw the root locus. And after that, create the TF just like this one. G z1 is equals to the 0 pole gain or K function in here, zeros z1, poles z1 and gain z1. Okay, these are the first system. And also we need to give the another system in here. Okay, this is the system 1, this is the system 2. Okay, and so we have only changed to the zeros -4 in here. Okay, because it must be changed with this effect, and then we can obtain to the effect of how we can manipulate the zeros or the transient response in the root locus. Okay, we can see that based on this criteria. Okay, and so Z2, Z2, Z2 and Z2. Okay, after that, as always we do for example, the percentage overshoot can be selected with a 25 divided by 100. Okay, and so it means that we only permits for this system to the 25 values for the overshoot. Okay, these are the condition. Okay, and also we need to select the zeta values in here, just like this one, sqrt divided by and divided by, and the log po square form in here, and pi square plus log po square. Okay. And after that we should run this code. Then the zeta is what? The 0.40. Okay, so how we can analyze the what? The root locus in here. Display root locus and figure to what? The subplot 1, 2 column and 1, and our locus should be given gz1, and the title can be given as the what? The root locus of -2 in here. And also we need to copy of all of these things in here, z2 and -4. Okay, these are the basic criteria for this case. Okay, and also we need to give the as grid in here to draw the line of the zeta. Okay, zeta, and also we need to give the y limit value for the what? The -20 up to 280. Okay, because the imaginary axis can be seen by the what? This range of values. Okay, and so if I run this code, and then we will have the what? The 2R locus or the root locus graph in here. Okay, first of all we need to see that we can push the left click in here, and so the gain is 50 and the pole is the what? -3 plus 6, and also overshoot values is equals to the what? 25, around that. But in the second place we can see that the gain is decreased up to what? Down to 20 values, and the overshoot is what? 24.9 or the 25. Okay, and so the frequency values or the natural frequency is changed or updated, but the zeta is constant at this case. And so if we add this condition in here, just like this one, and so the zeta line cannot change, but the our root locus is updated to the another one in here. Okay, and so the zeros can affect to the what? To region of these terms. For example, the pole -3, but in the second place we have the pole -1.87. And also we know that if the real part is smaller than this one is faster than the what? Than the -4 one. But in the second place we can see that this imaginary part is updated or decreased up to the what? The 4 value. Okay, and so this 6, this is 4, which means that we decrease the oscillation values on the second root locus if we increase to the what? The negative part of these terms up to what? The -4. Okay, and so if we can see that the exact values of these terms, and so we need to give the what? Find the proper value of the k. Okay, these are the gain for this case. Okay, and so if I choose the selected k z1 is equals to what? 51.25, and selected k z2 can be selected 20.70.60, because if we are run this code, and then this code can be seen as, if we getting the closing and closing and closing and closing values in here, just like this one. And so if I put these terms, and so 50.2 in here, and also we can say that we can see the root locus values in here just like this one. And so if I put these terms, and so this equals to what? The 20.3. okay, and so we can update the what? The 50.2 in here, and also the other term, this one. Okay, this is how we select the proper values of the overshoot in the what? In these two derivative term. Okay. And after that, the output signal in closed loop form can be written as CLTF Z1 can be calculated with what? The feedback of the what? The selected KZ1 times GZ1 unity feedback, which is equals to 1. And also we can give the Z2 in here, just like this one, just like this one. And after that we can draw the whole the results in here, the step CLTF Z1 5, and hold on, the step CLTF Z2 5. okay, and the title is the step response of systems. Okay. Read on must be selected in here, and the legend values -2 and -4. okay, and so if I rerun this code and then see that the first graph is the what is our cases of these terms. Okay. And so we can select that at this point and this point. Okay. And so -4 value is downgraded in here with the what? With these terms, because just see that the real part of the what? The root locus -2 is higher than to do this one. This is the -3 and this is the -1, and so we can see that our transient response is faster at the what? At the -2 characteristics. Okay. Also we can see that the -1.8 is the what? Is closing the transient response or increasing the transient response time in here. But we have the 4.21 and we have 6.65 in here, which means that this is the what? Our oscillation response. In the -2 we have greater oscillation in here, but in the -4 signal response we don't have this kind of oscillation. For example, we have the 2 oscillation in here, or 2 peak values, but in the -2 we have the 4 values. To what? To steady state characteristics of this system. Okay. And so we can easily analyze the system based on this information, but just remember that if we select another response or another time variable in here, for example, if we updated the overshoot value up to 10 or 50 or the 5, and so we need to select a new gain for this system in order to what? In order to create the proper values of the closed loop transient response. And so if we add the PI controller or the integral controller of these terms, and so we must update gain again based on these informations. Okay. And so we can easily analyze the what? The closed loop response of the R system based on this root locus techniques. Okay. So return to the session of the what? The PD design in the root locus techniques, how we can calculate our responses based on by hand, right? This is important. First of all, we must select the system, and we can write that the example of this session just like this one. The example, assume that you have a system like this one. The RS is the reference signal in here, just like this one, the minus, and we can create the ES at this time, but we have the K divided by S plus 4 and S plus 6 in here, and also we can get the output values of these terms in here, just like this one. Okay, these are the basic system. This is the GS, but the changeable or updatable coefficients of the its gain. Okay, and so our main question is that the design an ideal derivative compensator to yield 16% overshoot value, and TS must be equal to the 1 second. Okay, for this system, these are the basic question for the for the determination of the R solution. And so if we have two values in here, the TS and the 16% overshoot, and so we can select the the proper pole values in here. How we can do that? The solution is given by with the first of all, the look for root locus. Okay, because we need to design it. Minus zeta dot omega n is the R pole at the 16% overshoot, which is equals to the minus 1205. Okay, and so the TS is calculated with the the TS for zeta omega n, and so the for 1.25, which is equals to the 3.320 seconds. Okay. And so we need to divide these terms up to the 1.3 values, okay, in here, to equalize the results of the TS to the to the another terms. Okay, but how we can calculate the the minus 1.205? How we can find it? These terms in here. And so we need to copy of all of these things in here. Therefore, PD design must be given in here, just like this one. The PD design. I'm sorry. Okay. PD design for percentage 16 and TS is the 1 second, but around. Okay, and so first of all we need to give the or remove the whole of these terms in here, just like this one. Okay, and so we need to give the p values in here for the first time, because we don't have the any zeros value in the normal case, right? And 0 and minus 4 and minus 6, and this is the p, and this is also p, and this is the p, and p. Okay, After all, we need to copy of this overshoot values in here to calculation. Okay. This is equals to the what? The 16. Okay. It's the zeta. And so if I run this code, we will have the 0.5039. Okay, in here. So first of all, figure the R locus should be drawing in here, just like this one. Okay, and so the title, the root locus of uncompensated system. Okay, and as grid, the zeta value and these terms. Okay, and so if I run this code, and then we will have these overshoot values in here, just like this one. Okay, this is equals to what is around the 42.8, but in the exact manner we can closing the values of these terms. Okay, and so this is equals to 43.4, and so the pole, to see that, is equals to what? The 1 minus 1.2. This is the real part of the R system, and the imaginary part is equals to what? The 2.06. In the MATLAB calculation, it's the sensitive calculation, this is equals to what? The minus 1.205. Okay, just see that. And so also the gain of the what? The 43.4. Okay, and after that we need to update the what? The find the proper values of systems. The selected K on the P controller must possess with the what? The 43.4. Okay, just remember that. And after that we need to find out the what? The another terms in here. And so this is how we can obtain the values of these terms, just using the standard P root locus uncompensated system. And so we will have this pole location, and so this pole location is utilized with the what? With these terms, because this pole location is the real part of the R system. Just remember that the S1 and S2 in second order system just equals to the what? The these terms. Okay, and J in here. This is standard formulations. So the question asks about that, we need to update the R settling time system, settling time of this value up to what? The 1 divided by 3. And so for new settling time, which is equals to the what? The 3.320 divided by 3. And so we should calculate the what? Calculate the TS for zeta dot omega n, and so 1.107. This is coming from these terms. Okay, and so for zeta omega n, and so we can say that the zeta omega n must be equals to the what? These terms 3, 6, 1. And so in the precise calculation we need to calculate these terms. 4 divided by 1.107, and so this is okay. Okay. This is the new real pole. To what? To provide the 16% overshoot and provide the 1.1 seconds for the settling time. Okay, and so we need to update the R system to the what? To the new roots in here, just like this one. Okay, and also just remember that our second order equation coming from the what? To remember that HS, for example, this is the second order formulation. Omega n square, s square plus 2 zeta omega n s plus omega n square, right? And also the poles is equals to the what minus zeta omega n plus minus, and so omega n times 1 zeta square times I or j, okay? And so in this manner we utilize the zeta, and so this creates the what, the imaginary part of the R system. So okay, and so from the root locus geometry, just using the geometry, we can calculate the new pole, imaginary part VD and the real part, okay? And so how can we do that? For these calculations, first of all, we need to draw the what, the root locus. You can easily write or draw this in the MATLAB, but in the by hand calculation we need to write that just like this one, okay? And so we have the what, the minus 6 pole in the open loop system, minus 4 pole open loop system, and also we have the zeros in the open loop system, okay? This is how we can transfer the our algorithm or the our root locus in here, okay? And so we know that we have the one desired point in here, and the pole D derivative part must be equals to what, the minus 3 6 1 3, right? And so we need to add the what, the j term, but we don't know the WD value or the this value in here. How we can obtain this value based on these informations or the this geometry of the root locus, okay? And so we need to add the some zeros in here, because we design in here, we are designing the what, the derivative controls like this one. And so we should draw the line, we should draw the straight line, and we should also draw the line, and also we need to add the sum what, zeros value, but we don't know the values of these terms in here, okay? And so from the geometry we know that we have the theta 3 and theta 2 and theta 1, okay? And so this theta 1 is equals to what, 120 degrees 26. Just using the geometry you can easily calculate these things, but in the MATLAB you don't need to use that. But if you want to design the any root locus or the PD controller in here, we need to define the or using the what, the geometrical relation in here, just like this one, okay? And so if we use this nomination in here just like this one, and then we can also draw this line. This is the what? This is the zeros. Theta 0 compensator, right? And so as we know, we need to create the what, minus 3 minus theta 2 minus theta 1 and plus zeta compensator in here. 0 compensator must be equals to the what, the 180 degrees right? This is the basic condition for the what, for creating the stable root design or the controller design in the MATLAB. And so we know that we have the values of these terms in here in the real part, minus 36613, and so we need to find the what, the other VD value in here, just like this one. And so the VD must be calculated in with the what, 103 times tangential 180 minus 21 26, right? This is coming from the geometry, because if we find these poles in here just like this one, and so if we add these terms, and so we need to obtain the 180 degree values in here, okay? And so if we are using the tangential information in here for this one, because if we have the real part in here and the opposite or the vertical part is the VD, and the relation of these terms VD divided by 3.613 must be equal to this one. Just simple using the geometry, okay? And so this is equals to what? The 6139, right? These are the imaginary part or the VD part of the R system. And so our desired pole coming from the what? The minus real part 313 plus J 6193, okay? If we select the proper K value, and then we can obtain the what? The imaginary part and the real part, just like this one, okay? And so how we can do that? Just remember that we should provide this information in here. The poles angle and the zeros angle must be equal to what? 180 degrees, okay? And so in order to set these coefficients, this pole or the desired pole, we must satisfy that the minus 3 minus 2 minus theta 1 plus theta 0 close compensator must be equal to what? 180 values, okay? And so the summation of these terms minus 275 6, okay? And so if we should do that, we must select this value as the 95.6 okay? These are the basic calculation. And so if we know the angle values of these zeros, which is equal to what? The 95.6 degree in here, and then we can write that our solution is that 6.193 divided by 3.613 minus real part must be equal to the what? Tangential 180 minus 95.6, okay? And so our result is that we need to add the sum zeros to the what? The 3660, okay? Coming from these results. Where is it coming from? It's coming from just using the tangential properties of these terms. Just remember that, because we have in the height, in the graphical depiction of these terms, just can be seen that we have the what? 6139 dimension for this curve, okay? And so we have the what? At this point 3, 6, 13, and also we have the zeros, but we don't know the location of these terms. And so if we draw the what? This time in here, and we know that this is equals to what? The 95.6 in here, and then we can determine the position of these terms, because if we remove the 180 minus this term, and so we get the, for example, alpha degrees, and so this alpha degrees must be equal to what? The 6.193 divided by 3.913 minus nu sigma, right? And so this is the deflection, this is the deflection, and so this is the tangential information. And then we can see that our sigma c z zeros, compensated zeros, must be put at to what? To the 3 values, okay? And so these are the basic calculation of the what? Our algorithm in here. Just remember that. or but you may use this information also in here. For example, we have the zeta in here, just like this one. If we have the zeta, and so we know that zeta times wn must be equals to the what? These terms, okay? And so these terms divided by zeta, and so this the new omega n value, right? And also omega n value. And what's the values of the VD in here? Just like this one, the VD Vn times sqrt 1 minus zeta square. Okay, just see that if we find this information, and then VD can easily be obtained with the what? With this relation. But after that, we need to utilize the geometrical relation between these two of them. Just remember that it may seem a complex, but we are just using the geometry, guys. Just see that we have one condition, is that the whole degrees must be equals to the what? The summation of these degrees must be equal to the 180. And after that, if we have the real part, and also we have the imaginary part of these terms, and after that we just use the what? The tangent, sinus, cosinus to what? To exact location of the what? Of the zeros. Okay, and so how we can prove that in here? See, if we know right now the what? The location of the poles, and the PD design can be built with the what? Or with these terms, okay? The PD, and so RPD minus 3.006, right? And so 0 minus 4 minus 6, and the PD, and the PD, and the PD, and the PD, PD, okay? And also we need to figure the whole of this PD, and this is the compensated system, okay? And then if we rerun this code, and then at the second root locus we have the new updated system, just like this one, okay? This is the what? The adding the minus 3 values to our system. And so the R overshoot values is seen as the what? With the values of the what? The 47.5. And so just see that the poles minus 3, 6, 1 and 6.19, right? And so what's the selected values of these terms? Selected KPD is equals to the 40.5. Okay, 47.5. These are the PD design. And after that, how we can create the closed loop response? CLTF P is equals to what? The feedback, unity feedback in here. Selected KP, right? Times GP and 1. And also we must update PD, okay? And also the figure, the step CLTP, okay? Hold on, and step CLTF PD, and title step responses, okay? Grid on, and the legend is equals to what? The uncompensated system and the compensated system, okay? Just remember that this selected K, P or PD coming from the what? The R locus with a specific pole location. And after that, what we have done in this system, just see that, for example, the characteristics of the peak response. First, we need to analyze it. In the uncompensated system, we have the 15 overshoot. It's closing to what is 16 value in the uncompensated system because we select the proper K value in here. But in the compensated system, we decrease it to what? The 12 value. 12 overshoot in here. This is why we have the closed loop transfer function at what? At higher than second order. In order to understand that, we need to write this code in here, just like this one, okay? And so just see that this code is the what? Is the third order. This is not the second order. If the third order, and then maybe our overshoot, small differences can happen in here. But in this case, we have third order system, and also we have the zero term in here, just like this one. This is the highly different between with the P1 or the second order one. Just remember that. And so if I rerun this code, and then we will analyze the closed loop response of the R system, the characteristics of the peak response in here, and also we need to check the settling time in here. In the first place, we have the 3.47, and so our objective is that we need to divide this term up to what? The 1.3, or the 33% of this settling time should be achieved. Just remember that 1.15, which means that if we are multiply these values with the 3, and so this is equals to the 1, we degraded the settling time up to what? The 1.15 values in here. And so we have the results of the RPD design in here. It's accomplished based on these informations, okay? And so these are the MATLAB example in here, but we need to return to the R nodes in here. In summary, in the PD design, is to what? We have the RS signal in here, just like this one, minus, and so we have the K1 in here, and we have the K2 times S in here, and we collect the whole terms up to what? Up to the lengths of this signal, and so we generate CS, and so we can obtain what? The unity feedback signal. And so the controller S can be defined with the what? With the K1 plus K2 S, which is equals to what? The K2 times S plus K1 K2. In this case, how we can find the K2 and K1? Just remember that in the second place we have the what? These terms, right? 47.5, which means that these values equals to the what? 47.5. And so this is also is equals to the 3, right? Because in the system we have S plus 3, right? And so the K2 is here in here, just like this one. 3 K1 K2 and K1 must be equals to what? The 3 times K2, okay? And so these are the basic coefficients of the what? The PD controller design. And so if you want to implement this code based on this information, and so we need to select the K2 as the 47.5, and K1 must be updated with accordance with these values, okay? This is important because in the real life application GS is already there, okay? It's a continuous system, but we need to design these parts by using the electronic or the softwares in here, and then we need to build these coefficients, okay? We just don't use the root locus or any other techniques in the real life or the real-time application. We just select the K1 and K2, and after that we apply the system to these coefficients based on the what? The error signal in here, okay? Yes. And so error can be obtained with the R minus C in your software, and then K1 is selected to K2 and K2 is selected 45, and also the GCS, or in time domain, K1 times K1 error plus K2, the error dt is fed into the what? Into the R controller signal, or the motor, or the torque values. Okay, and so this is how we can achieve the what? The PD design in the what? In the root locus techniques. Okay, in the next lesson we will talk about the what? The PI and PD comparison, and after that we collect, or we connect the PD and PI in order to what? In order to build the PID controller. Okay.